In Physics 251, we have the additional tools of dealing with calculus, and if acceleration is not constant, we have ways of dealing with it using derivatives and integrals, or antiderivatives. In 151, we have a little bit more difficulty with that since that math is out of scope for the particular course. And so the question is, how do you deal with if acceleration is not constant? So I know that the average acceleration is the change in velocity over the change in time. What about the instantaneous acceleration? Well, if I have a velocity time graph that's curved like that, this is not constant acceleration. Constant acceleration for the velocity time graph would be a straight line. So this is acceleration is constant, and this is non-constant acceleration. Well, we can find the acceleration at any particular point by just taking if I want to find the acceleration there, you draw what's known as a tangent line, and then you find the slope of the tangent line. You basically turn the curve into a straight line. This is the essence of a derivative. If I know the equation of this, there is a pre-calculus way of dealing with that, but that really don't want to get into that in Physics 151. If you know how to do it, more power to you. So if acceleration not constant, in other words, velocity graph is a curve, then you would find the acceleration at a point by just taking a tangent line, a line that just barely skims at that point, and you would find the slope of that line, rise over run, or whatever technique you happen to be using. But suppose you're given acceleration time. If this is acceleration versus time, well, I know that the velocity time is the area underneath it, so let's make this change in velocity versus time. And so it starts out with not much change here, and then as you go for a particular time unit, we get more and more change, and so velocity actually will do something like this. So we start out with, so if these are even time increments, notice this area here is smaller and the area gets bigger as we go, and so the change in velocity for equal time increments, not much change, then you have more change, and then you have, oops, if I do that right, and then you have even more change, and it will continue to increase. But finding, suppose I want to find out what is my average velocity. Well, the reason this is change in velocity is because I need an initial condition, so let's just assume that the initial velocity is 0. How do we find the average velocity for something that is curved? Now, if it is not curved, then the average velocity is just smack dab in between the lowest and largest value of the velocities. But if it is curved, it's a lot more difficult. So if I want to find the average velocity in, say, this range right here, well, you're looking for, mathematically, if I know the area underneath this curve here, you're looking for the value such that that value times this time interval has the exact same area as this. So the average velocity times the time interval is equal to the area under curve for the same time interval. So same initial and final time. And you would have to do sort of a crude estimate in 151. Now there is a place where we can deal with non-constant acceleration and not have to play around with estimating. And that's if my acceleration versus time graph is actually two constant values. So I know for the first time interval, so if my initial velocity is 0, during this time interval right here, you have constant acceleration, and then you have a second constant acceleration problem. So you would treat this as such. So if this is, let's say that's meters per second squared, and that's meters, and that's 10, seconds, and that's 10 and 20, then initial velocity is 0 during this region right here. Oh, I have to give a number here. Let's make that 5 meters per second squared. So that area is 50. Let's make that 7. This area right here is 10 times 7, or 70. So my change in velocity is going to be 50 plus 70, or 120. I started 0, so I end up at 120. So we can find average acceleration. So it's somewhere between 5 and 6. So the average acceleration is the change in velocity over change in time, which is 120 meters per second over 20 seconds, which is 6 meters per second squared. It is halfway in between those two, but that's only because our time intervals were the same. So let's do that slightly differently here. Let's put this at 5 and 7 again. This is my acceleration in meters per second squared and my time in seconds, and 10. And let's make this 15. So this has an area of 50 meters per second. This has an area of, that's 5 times 7, or 35 meters per second. So my average acceleration is, well, my total change is 85 divided by 15, 5.67 meters per second squared. Average velocity still becomes trickier. So after 10 seconds, I'm at 50. So I'm going to start here. This actually would be constant. So that's 10 seconds. So that is straight. So that is 50. And then at 85, because that's my final change, that's at 10. And this is my velocity in meters per second and time in seconds. This would be 15 seconds. And so it is should be steeper. I'm not to scale here. So my total area under my curve here, well, I've got a triangle here. This is 1/2 times my base times my height. And I have a trapezoid here. So this is 1/2 times my base, or my height there, whatever, however you want to look at it, times the average of those two. That's where the 1/2 comes in. So it's 1/2 of 50 plus 85, 250 plus 337.5. So the total area under the curve is 587.5, and that would be meters. So that is the total displacement over the course of this, assuming, again, we start at 0. If we started at something else, this curve would just be moved up, and so you'd have an additional, going faster to start with. And so, but the average velocity is the displacement divided by the time. So 587.5 meters divided by 15 seconds. And so on average, you're going 39.167 meters per second. That is the average